Good morning, everyone, and thank you for joining our webinar on Concentrate-to-Carbonate DLE Eluate polishing to conversion. So just some quick housekeeping rules before we start. As always, we're going to keep mics and video off. However, we would love it if you have any questions or anything, please feel free to use the chat. At the end, there will be a Q&A session. And as always, the webinar will be recorded. And then sometime this week, probably this week, we will have it up and available on our website. So the production of DLE eluate is the first important step in producing a lithium product. The final quality or purity achieved in the DLE production process dictates whether the product will be sold as a battery grade or technical grade. The difference in purity between battery grade and technical grade is very small. However, the selling price between them is significant. We are so happy that you've joined us for our webinar as we discuss the post-DLE processes of eluate concentrating, polishing, and conversion, and the various methods used in achieving a battery-grade lithium product. So before we start, before I give the floor to Grant, we have two polls. I would like to launch the first one. So the first one goes as such: how many people are in the process of designing their post-DLE process? So either yes or no, if that is where you are at. I'll give everyone a minute. Okay, we're 50-50 on this one. Oh, so a lot of people are. Perfect. That's great. And then our second one. Oh, sorry, here, I'll launch it. Or could I, here, I'll just edit it quickly, sorry. Here we go. And so the second one is now launched. So how many people are considering ion exchange or electrodialysis for polishing? I am or I am not. I'll give a couple seconds for that. Okay, so Grant, I noticed your mic is turned off. So just, I think we're ready to start now. I am going to pass it on to Grant, who is our VP of Solution Sales, and he will be hosting the webinar. So Grant, the floor is yours.
Great. Well, thank you very much. I appreciate everyone participating today. I will start the webinar. Oh, I should share my screen first, shouldn't I? Sorry, I apologize for that. Always a little. There we are. And if you can just let me know if you can see my screen, that would be great.
Yep, we see everything great. It's perfect like that.
Okay, great. Well, thank you again, everyone, for attending this, I'm going to say, series of webinars regarding DLE processes, starting from pre-DLE to DLE to post-DLE. Today, what we're discussing is concentrate-to-carbonate, which is a post-DLE process. So if you have not attended the previous webinars on pre-filtration, conditioning, and DLE media selection, please feel free to go to our website and take a look at that. But today we're going to be taking a look at post-DLE processing. So what we talked about is using direct lithium extraction media for lithium extraction. And some impurity removals, such as, I'm going to say, solids, or maybe some filtration. What we're going to be talking today, that was the previous webinar, we're going to be talking about post. So just quickly, I'd like to kind of recap kind of what the DLE webinar was about, because it has some beneficial information to understand, which will help facilitate the understanding of this webinar. So what is direct lithium extraction, or DLE? It's a process of directly removing lithium from a brine source, such as geothermal or petrolithium, or other sources available. DLE media is typically ion exchange, which is a resin or absorbent. The complete train, as I said, is kind of a pretreatment DLE. Post-DLE is concentration, polishing, concentration. One of the key factors in selecting DLE media, of course, is the lithium selectivity, meaning that the DLE eluate contains a small amount of contaminants. So the selectivity, I should reference that being more so purity. So lithium selectivity is how well it can remove the lithium. Purity is not only did it remove the lithium, but did not remove any other contaminants. So you want to minimize any contaminants being washed over or eluted over into the eluate. So why is there difficulty in DLE? Why isn't it just straightforward? Well, there's a couple of reasons. One is that we're using a hypersaline solution and there's competing ions. And when we take a look at the periodic table, you can see that lithium's here, but commonly what's referenced within DLE efficiencies and processing are these ions: sodium, potassium, magnesium, calcium, because they have the affinity to want to go onto the exchange site that the lithium wants to go onto. So you can kind of see from, let me just minimize that, from this is that these are a little bit more difficult to remove and differentiate within the media than these other ions, which are easily rejected and will pass through on the depleted brine. So this is kind of the challenge that everyone has, no matter what their DLE media is, whether ion exchange or absorbent, is because of the similarities in the ionic strengths of these particular ions. So when we talk about that, I'm going to say simplified process, media is exposed to lithium barium brine. The media, when you load it up, it reaches equilibrium, meaning it's fully loaded. It doesn't, when we say fully loaded or saturated, it doesn't necessarily mean that it's all lithium. It can be other contaminants, such as magnesium, calcium, sodium. So depending on the ion uptake mechanism, there will be a mix of cations. Of course, what we want to see is we want pure lithium coming out through the eluate, but of course we know that isn't reality. And what we get is a ratio of magnesium, calcium, and sodium. What we're seeing here is that the competing ions, so you have an ion exchange and it has a functional site. Think of it as a magnet that's going to attract the lithium. But other ions, which are similar to lithium, are also going to compete and try to get onto that site. When we take a look at the affinity or the attractiveness to get onto that site, you find that magnesium has the highest affinity or challenge of the lithium sites, and calcium, sodium, and potassium. And this is why you see when you take a look at DLE efficiencies or testing that you typically don't see a complete analysis of all the ions. You kind of see these bulk or the main ions being examined, because this is what's going to challenge the efficiencies. Alkali metals and alkaline earth, you can take a look at those. And just when we take a look at those competing ions, we typically reference them. We ratio the contaminant against lithium to see what those ratios are. And that gives us an indicator of how much of a challenge they're going to be. If it's a low ratio, then great. Then there's more lithium than that contaminant. That's going to be easier to resolve on the polishing side. But if the ratio is switched, it's going to be more of a challenge. That's why it's really good to take a look at what these ratios are. So getting into the types of DLE media, you'll see an ion exchange, whereas there's a functional group where the lithium will be, just the lithium will be absorbed into the ion exchange media. And then there's absorption materials, which will be the lithium chloride will be absorbed onto the surface of the medium. So ion exchange is into, absorption materials are onto. Difference between the two, basically they're functional or material groups. You'll see aluminum-based, magnesium-based, titanium-based. All depends on what type of contaminants you have and what you're trying to achieve. one may be better than the others. To elute, once you've loaded up the lithium, well, I've got to unload the lithium. So you're going to elute that with a reagent. And typically in those ion exchange, you're going to use acids. The difference or uniqueness with sorbent material that I can use typically water to elute the lithium off. So in some cases that a sorbent material may be preferential over an ion exchange, or vice versa, depending where you are. Lots and lots of DLE media suppliers out there. These are just a small fraction of them. So when we take a look at the post-DLE process, there's kind of two ways of taking a look at this. Is one, when you take a look at removal of lithium from the brine, consider it that it's a lean feed, meaning that we don't have a high concentration of lithium, and we're going to extract the lithium directly from the brine. Once it's been removed, then we have a depleted brine, which is typically returned and returned back to the reserve through a reinjection borehole. So in this process, when you have a lean feed, which is the DLE, is that you're extracting the lithium from the bulk solution. On a post-DLE side, you're now talking about more of a rich feed because we've concentrated the eluate. And when you concentrate, of course, you move water, you not only increase the lithium content, but you also increase the other contaminants. So it is a rich feed we're trying to polish the lithium from. In that particular instance, what we're doing is that removing X from the bulk solution, that we want to keep the lithium, but we want to remove the contaminants. So it's a selective transport versus a selective entrapment or removal. I hope that makes sense. So this is what we're going to be focusing on today, is the post-DLE operation of polishing, of removing those contaminants. So on the post is that you've taken your DLE media. I've eluated, and now what I'm going to do, conditioning may be filtration, it may be such as removal of organics or other contaminants, it may be some removal of calcium, magnesium, different things. What we're going to be taking a look at on the post is assuming that there is no eluate conditioning, but we're going to take the eluate, we're going to concentrate the eluate. Typically the DLE coming off of the DLE, the DLE eluate is typically significantly lower in TDS. Your lithium brine source may be up at anywhere from some 60 to 200,000 to 300,000 ppm TDS. Remember, you're moving the lithium directly from the brine. We're going to have hopefully minimum contaminants coming into the eluate. So that means that I have a significant drop, or I should have a significant drop in my TDS. So where we see, let's say 100,000, I'm going to see 5,000, maybe 10,000 ppm TDS over here. So relatively very, very large drop. The concentration side, I'm very interested on concentrating out my lithium. We'll get into why that's important as we get into the polishing side, why it's important to try to maximize your lithium as much as possible within that stream, polishing, removal of contaminants. And finally, if everything's been done right, we're going to convert to battery grade lithium carbonate or lithium hydroxide. That's the end goal. That's the goalpost, and when you hit that that section, there's usually cracking the champagne and the cheers. So on DLE eluate concentrating, there's lots of technologies out there in which to take a look at. Some are maybe more beneficial or preferential than others, depending on your geographic location, cost of energy, environmental restrictions, ESG requirements. All those things come into the process of selection of what is going to be the technology of choice for eluate concentrating. So conventional technologies that's been around for a very, very long time. It's thermal evaporators, so it's using a heat source essentially to heat up, pressurize and heat up a bulk fluid in which I'm going to drive water off through a distillate and then cool that. And by driving that water off, that's how I'm going to concentrate. Evaporators have been around for a very long time, well understood, but the challenge is that they have a high energy component to it. And then on the OpEx side, because of the high temperature, high pressures, and the very high fouling and corrosive environments, they have a very, very high maintenance or OpEx component to them. So not only on the CapEx, but the OpEx is significant on them. Technologies change, chemistries advance, material sciences advance. So now you get into additional technologies. I have not, just so you know, touched on crystallizers. I mean, that's a kind of a form of thermal evaporators. Typically, crystallizers are going to take very, very high concentrations and then convert that to a dry solids. The only thing we're considering in this webinar is that we're going to take the eluate. We'll continue. We're not going to go to a zero liquid or a dry. We're going to have high concentrated lithium carbonate or lithium hydroxide and not a powdered. Membrane distillation, this is a new technology that has been in the laboratories for a while, but slowly is evolving and getting to the commercialized stage. Essentially, you're using, think of it, two technologies, a hybrid between a heat exchanger and membrane process. You're going to take the fluids, you're going to heat them up, and you're going to, the temperatures and pressures are going to drive water through the membranes. The technology is evolving, it's getting better. In my opinion, there's still some challenges to it, and we'll get into that. The energy is still a little bit high. It's I'm going to say the OpEx, again, the fouling of the membranes, which is a bit of a challenge, and the CapEx is a little high. Typically, you find membrane distillation in cleaner applications such as pharmaceuticals, microelectronics, but they are slowly coming into the lithium brine market space. Next is high recovery reverse osmosis, RO. RO is I'm going to say, the gold standard within the industry. Whenever you can use an RO, you typically want to use that. The challenge with RO is that they are osmotically limited, meaning that you can only take the TDS so high. And what restricts is that the osmotic pressure will restrict the TDS from going any higher. So for example, for seawater desalination, which is TDS between 35,000 to, let's say, 40,000 ppm, that because the high TDS, you have to have significantly higher pressure. So you operate around 1,000, 1,200 PSI. There are advancements in material sciences from DuPont Hydronautics that now have offer membranes operating in the ultra high pressure range, which correlates to 1,700 PSI, very, very high. And that at that pressure, you can take the TDS up to 140,000, 120, 140,000 ppm. But that's it. That's the limit. You cannot go any further higher than that because the material restricts you from doing that. You could go higher if the materials would allow a higher pressure or operation. But right now, within the commercial industry globally, that the maximum you go is 1,700. So that means that the highest TDS you can go to is 120, 140,000 ppm. Forward osmosis has been around for a while, excuse me, or industrial forward osmosis. And what osmosis is significantly different from, thermal evaporators or RO, meaning that it is not a pressure-driven device and doesn't require high temperatures. As such, if I don't require high temperatures and high pressures, then my operating energy is going to be significantly lower. And this is where industrial FO is entered into the market space. With the advancements in material sciences and processes, that FO is now is now an acceptable technologies for concentrating. So you take a look at, thermal evaporations or evaporators are 16 to 25, I'm sorry, 16 to 25% TDS. Crystallizers, as we expect, to be higher. Membrane distillation, 16 to 22. RO recovery, again, your pressure restricted is 19 to 20, and forward osmosis is 10 to 24%. Why is this important? Because when we take a look at TDS, we want to, as we extract water, we want to maximize our TDS, because that maximizes a concentration factor of the lithium. So there is a cross-reference of the Eluate concentrating technologies. If we dive into them a little bit more, we take a look at thermal evaporators. I mean, a relatively easy concept to understand is that we're going to take a brine in, or a solution in, and I'm going to pressurize it, I'm going to heat it, and I'm going to drive water. I'm going to distill water off that. We take a look at the top of this. This is typically a calandria. And all this is can be different configurations. It could be vertical, it could be horizontal. This is a vertical calandria, meaning the tubes go vertical. And how this occurs is that you fill the top of the calandria, has a bunch of tubes, open-ended tubes, and the solution flows down the tubes. And as it flows down the tube, it creates a thin film of that liquid or solution on the inside surface of the vertical tube. And on the outside of the vertical tube, we have a steam inlet. So it's a heat exchange. So the outside of the tube is being heated. The heat or energy is being transferred through the metal pipe to the thin film. And the thin film, in turns, volatilizes, converts from a liquid to a gas. Pure water comes off. The concentrate drops down to the bottom. As you see here, falling film is that steam goes up. It's captured, it's separated, and the concentrate outlets down there. So a very straightforward process. There are straightforward process, but there's lots of different types of configurations and operations of them. Essentially, a lot of them, most common, is that you're going to have a steam boiler firing up to put steam into where the calandria or vertical tubes are. And that's going to be the energy or the heat thermal energy required. Types of, I'm going to say categories of thermal evaporators are falling film, nucleate boiling, flash evaporators, direct contact. You can take a look at those in a little bit more, but essentially it is heat transfer into the solution to cause the water to distill off. Another types of thermal evaporators are multi-effect evaporators, or MEE, multi-vapor recompression, whereas you have a vapor and I'm going to recompress that, and then this is then going to feed over. This is what this picture represents. Sorry, it's an MEE process. And then thermal evaporator recompression. There's more variables to that, but essentially it is a heat exchange process. So you're taking a bulk fluid and you're heating it to distill water off. It's a technology that's been around for a very, very long time, but the advent of, I'm going to say, ESG, higher energy costs, has driven the advancements of additional or the evolution or advancements of other technologies. Just quite quickly, if you do have a thermal evaporator, this is kind of what you're looking at. It is critical that the heat exchange surfaces remain clean. If you had 1/16 of a film, a scalant or foulant, that can significantly reduce the efficiency in operations of the vertical falling film tubes. So typically what you'll find is that on a regular basis, once a quarter, or whatever the operations is, this is just simply, this is a rotating wire brush, and essentially you're going to insert that and you're going to go through every single tube. So this is what we refer to in the industry as punching the tubes. So if you have a chiller, the same thing. In this, it's a calandria. You got to punch each of those tubes, and you kind of see right here, you kind of see some corrosion products. Again, these are very corrosive or aggressive environments, so that's common to see some type of oxidants to come through. But that's key to maintain the efficiencies of regular maintenance and punching of the tubes. Membrane distillation, very similar to a thermal evaporator, is that think of it as a heat exchanger. So I'm going to, the brine is I'm going to heat up on one side and it passes through. And as it gets heated up, what happens is that water vapor will pass through a semi-permeable membrane and be collected onto this side. And then we don't want that pure water because it's being heated up here. We have a feed solution which needs to cool it down to maintain this. But if I allow this, if I didn't have this, I'd have thermal runaway. So therefore, I also have to have cooling water associated to maintain this. Quite simply, there's lots of variables. I'm not going to go into each one of them. Temperature gradient is critical. Remember, I've got a bulk fluid. I'm heating this up. It's going to pass through membrane, so you can kind of see that it's hot and it's going to go cool. So there's a temperature gradient that occurs here. Just like a thermal evaporator, if I get any type of foulant or scaling occurring on this side of the membrane, it significantly changes the heat transfer coefficient. So it drops very significantly. So it is critical that on membrane distillation operation, that the membrane surfaces remain very, very clean. So that may require a continuous online feeding of chemistries to prevent foaming and deposition or scaling. Just like thermal evaporators, lots and lots of different types of membrane distillation types. Some are still in the evolution. Some have been commercialized. Talking about air gaps, conductive, but they all operate the same way. I have a hot side, I have a cool side, and the heat is going to drive the water vapor across the semi-permeable membrane. So taking a look at this, as I said, is you've got this hot feed, cold feed, and then you have this temperature drop gradient across. So a temperature polarization is key on the membrane side. This has to be remain clean. If you keep clean, then you get some half decent water recovery coming off of this. Next is forward osmosis. Very much different from thermal evaporation or membrane distillation, which requires heat and sometimes pressure, particularly on the thermal evaporators. Whereas forward osmosis or industrial FO uses a draw solution or a salt in which to attract and transport water across a semi-permeable membrane. Difference here is that there's no external pressure, there's no heat, and there's nothing to drive the water across except the solute acts as, think of as magnets. It literally reaches across and draws water across into it, and water will move from a high concentration to a low concentration. So this happens, this is what plants, animals, and the cells in your body, how it operates. You know, how does a tree get water from the roots up to 100 feet into the leaves? It's through osmosis. It's free and spontaneous. It's free energy, it's spontaneous. However, you have a salt solution. I don't want that. And that's where the energy requirement comes in, is how do I separate the salt from the water in order to have a high purity, which I can reuse back into my process. Forward osmosis, the type that we use is how do we separate it? Once we have that salt solution, we run it through a stripping column. There is the salt that is used. It will transition from a liquid to a gas. When it goes through a gas, it leaves solution, pure water is left behind. That's ejected and reused back in the process, and that the concentrate is then, that's the eluated, the concentrated eluate, which we're now going to use for our, to run through the processing and through conversion. This is just a simple process diagram of an FO, membrane, stripping columns, and absorption. Typically FO, for the operations of it, we typically run it with an RO. The reason being is that the FO can take the full eluate volumes at low concentration. However, remember that we're always looking at the economics of the DLE process. If there's some way of reducing the energy, the capex, or the physical footprint, and the opex, we want to do that. So what we do in FO is we typically use a reverse osmosis, maybe at a high pressure at around 1,000, 1,100 psi. What that does is RO, which operates about 2, maybe 3 megawatts per cubic meter of permeate. That will concentrate the feed, and by concentrating the feed, that reduces the volume going to the FO. Reduced volume going to the FO, meaning that's less I have to concentrate or treat. That means a significant reduction in capex and opex. So that is concentrating. So through concentration, we use conventional thermal evaporation, membrane distillation. We can use industrial forward osmosis, and those are pretty much the most common ones. Now that we have the eluate, we've concentrated the eluate. Now we want to take a look at, my next objective is, okay, I need to produce a battery grade lithium carbonate or lithium hydroxide. And what we mean by battery grade, not technical grade, is battery grade requires a purity of 99.5% purity. That means that the bulk of the lithium carbonate or lithium hydroxide is lithium with very, very minor or trace contaminants within that, within the final product. So this is why polishing is such a critical component, is because in order to realize, I'm going to say to achieve a battery grade lithium product and command a very high return, I think it's going around 40,000, maybe 60,000 per metric ton of lithium carbonate equivalent right now. In order to maintain that, to realize that, you've got to get it to battery grade. So DLE eluate purity, we talked about selectivity, which we know is that this is going to select the lithium and pull it out of the brine, but really what we're focusing on here is what the eluate purity is, meaning how many contaminants or the concentration of contaminants coming over or in that eluate. And remember, because we've concentrated, we've removed water from the eluate that to concentrate it. That means not only did we concentrate the lithium, we've also concentrated the contaminants. Now, depending on the operation of the DLE, if it's able to produce a high purity DLE eluate, then that's great. Then really it's trace polishing, meaning I've got a lot of lithium and a little bit of contaminants. Whereas bulk means that I've got, a lower amount of lithium, but a higher amount of concentration. So that means I've got a bulk of contaminants I have to remove. So that's a common terminology that we use in DLE polishing. Is it a bulk contaminant removal or trace contaminant removal that I have to accomplish? By definition, bulk ion removal is considered anything greater than 1% of total dissolved solids, and trace ion removal is considered anything less than 1% of TDS. So the challenge sounds pretty simple. Ion exchange, if you've got, let's say it's a softener, hey, we load it up with salt, we run it through and it softens it. That's great. Softenings have really, really high efficiencies. The challenge with brine is that you operate in a hypersaline solution, a very high TDS. And when you operate in that type of environment, it changes the thermokinetics and the thermodynamics and the kinetics of ion exchange. And therein lies the challenge of doing polishing in these hypersaline solutions. Resins will react differently than low-level TDSs like potable water. So it takes a little bit of I'm going to say skill and a little bit of testing to really validate select and validate the right ion exchange to be used in polishing. So the high concentration of contaminants, I say, may affect the efficiency of the competing ions. So very high divalent content. So I have my DLE eluate. I have not only my lithium, but some contaminants. Most of the contaminants you typically find are going to be calcium, magnesium. It could be potassium, some boron, and so on. But for this discussion, let's just focus on calcium, magnesium, which are divalents after we elute. If we have a really high concentration, meaning that the purity of the eluate not that good in relationship to other DLE eluates, that we may have a bulk removal. So therefore, there's kind of two options that we may want to consider. If it's very high, we may want to consider physical precipitation because it is going to be more economical than ion exchange. So what do I mean by that? Is that if we have a really ion exchange is great, but if I have a very, very high concentration and I use ion exchange, and the ion exchange is going to reach in and pull that out, and it's going to load up very quickly, the amount of regeneration this is your ion exchange resin vessel is going to have to go through is going to be significant. So it's not only important of the loading of the resin, but because you're going to be regenerating so often, the regeneration cycle becomes even more important than the actual loading of itself. So if it's very high, we typically want to avoid ion exchange because the regeneration cycles are going to be very, very short. You're going to load fast, which it means that you're going to be going through a lot of regeneration, which means that you're also going to be using reagents to regen with. So now I've got my chemical consumption's gone up and my chemical waste stream volume is going to go up. So that's why I've said that another option is physical precipitation. You can do it with ion exchange, but the economics of it may dictate physical precipitation. Another technology that's actually evolving and getting better is nanofiltration. It's getting better at rejecting the divalents, getting tighter, so a higher percentage of rejection, and getting better at lithium retention, of course, which is the product we want at the highest yield. So therefore, we want to retain as much lithium as possible. So let's talk about physical precipitation. If I have calcium magnesium, to precipitate that, physically precipitate, I'm going to react it with, let's say, hydroxide and carbonate, so like a soda ash. And that is going to cause the reactant, the products will then, the reactants will create the products of calcium carbonate and magnesium hydroxide, and it's going to hit the solubilities and it's going to drop out of solution. So part of that physical precipitation, I'm going to have a physical removal. So it could be a filter, it could be a DAF unit, it could be an inclined lamella that has to physically remove those solids. Very common is soda ash or lime. Nanofiltration, you may find that in the DLE process flow sheet. It's very effective at removing divalent ions. It's great. However, it doesn't remove 100% of the calcium and magnesium. There's going to be a little bit of trace. If it was a sulfate, just so you know, large molecule, it's going to reject everything. But calcium magnesium does a great job of removing the bulk, but you're still going to have some trace contaminants. So you're going to have to, that will be addressed through the polishing. But the other component from NF is that it does reject a percentage of the eluate or the concentrate. So not only will it get rid of those divalents, which is great, that's the objective, but you may also lose some of the eluate, which contains lithium. So that needs to be balanced significantly on the economic, needs to be really modeled out to see if it's the economics and use of nanofiltration can be justified. So now that we've taken out, we've concentrated, we've removed kind of the bulk through precipitation or nanofiltration. Now we're getting down to the polishing. The polishing is that, as we originally talked about, is selective entrapment, which means that we're going to be removing the contaminant from the bulk. So the eluate should consist mainly, or the highest percentage of lithium and a little bit of contaminants. And these are the contaminants X that we want to remove. So how do we do that? Well, we can do it through ion exchange, selective extraction of the impurities, depending on the type of impurity that we have, whether it's a divalent or maybe it's boron. We can move boron up to be a selective material. That will dictate the type of ion exchange material we need. Now, we may have more than one type of ion exchange vessel. We may have, I'm going to polish it for calcium magnesium, and then I'm going to polish it for another contaminant removal. So you could have a train of ion exchange depending on the type of contaminants that we need to remove and selectively remove from the eluate. Just remember, I'm going to state the obvious, is that ion exchange removes ions, so it has to be ionized. Doesn't really remove non-ionized materials very well. The other component is the ion exchange. Once it's been loaded, you've got to regenerate it. So the other thing to consider is not only the loading, yeah, that's great, it's going to remove the contaminants, but what is the reagents that I need to use to elute, or sorry, regenerate the resins, because that is, not only is that a cost, but I'm also going to have waste to consider. Another, I'm going to say, evolving technology is electrochemical or electrodialysis, which uses it uses the charge of the ions, an anode and cathode, and if I have an ion, I can actually attract, whether it's a positive or negative, pull them across a media, ion exchange, so it'll kind of leapfrog across this, and then pass through a semi-permeable membrane. So I have an ion exchange resin configured with a semi-permeable membrane. And the evolution, I'm going to say, the efficiencies of electrodialysis is increasing significantly. And there's a lot of commercialized electrodialysis systems out there. There are some limitations to it, but as an overview, the two main ones to consider is ion exchange, and also, depending again on the contaminants, is electrodialysis. So polishing removal of the ion exchange depend on what we have. There's different types of resins available. As you see here, is that I have, the way that this works is that there's a charge, and it's going to go onto the resin, and depending whether it's a monovalent, a single charge, or a divalent, will have dictate the selection of the resin. But also, when you get down to trace versus bulk, also there's some challenges associated with the selectivity of a contaminants being removed, and we'll get into that in a second. So ion exchange only remove ions, not substances. I'm sorry if I've stated that. I sometimes get this question a lot. Well, what about removing silica or boron? Well, you can if it's ionized. So what does a resin look like? Well, ion exchange resin, there's a gel or a macroporous. Those are the two most common. These are uniformed. You can kind of see a bead shaped. You can typically tell gel resins, they're kind of translucent. So if you ever mix up your resins and you're testing them, you don't know what's what, just remember that gel resins are translucent and macropore resins are opaque. So that's a quick way of differentiating what you're looking at if you're looking at two beakers of them. The gel resins typically have a higher, I'm going to say, loading capacity than the macroporous. However, that gel resins have a tendency that they will degrade faster, have a shorter lifespan than the macroporous resins. So again, you're going to weigh the pros and cons of the two. So different types of resins and different structures of resins, of course. And then because of the structures, that will dictate life expectancy, OPEX, and CAPEX of those resins. Gel resins are typically a little bit less expensive than macroporous resins. However, the macroporous resins will have a longer design life. So again, considerations when you're doing the economic evaluations of the two. So ion exchange selectivity, this is important. It's a mathematical concept to explain how much resins prefers one ion over another. Again, we have lithium, but we also have lots of other ions in there. So how do we ensure that one ion is going to be removed or is going to be selectively removed from another? So Helfrich attributed selectivity to swelling pressure of the beads. That's kind of maybe a difficult concept to wrap your head around, but it is there is a finesse to that. So as the bead loads, it swells and forms it will swell and create a pressure. So the more pressure we have, the less that it can load onto. The simple theory is that another concept to selectivity not only is the swollen form or the internal pressure, swelling pressure of the bead, but is, think of a lock and a key. Is that some ions just fit better into those exchange sites than others. So in some instances that a divalent will require two ion exchange sites or exchange sites to fit, and also the size, the ionic strength of that ion may be precluded from going onto the site. So this is why the ion exchange simply fit better than others. When we take a look at DLE materials, from not only do I want the lithium, but the sodium, I have sodium, potassium, calcium. Those ions have a tendency to fit well into the same lithium slot on the bead. So others can't. So the valence number or the charge is important for divalent ions versus monovalent ions on selectivity. And selectivity, another for polishing, for trace, an important concept to remember is selectivity changes with concentration or TDS of the solution. So TDS, particularly in trace polishing, can have a significant effect on the efficiency of the ion exchange. So a quick way of taking a look at selectivity is, I borrow this from the internet. I thought this was quite relevant, is small and fast versus big and slow. So what does that mean? It means that certain conditions will favor a small ion and will work fast, meaning high space velocities or short empty bed contact time, meaning it's going to load very quickly, and high ionic strength in an environment of low TDS. And that favors the small ions with a fast load rate. Conditions that favor big and slow is that when you have low space velocities and low ionic strength. So the other component, when you take a look at the ion exchange, we said that some ions fit better than others. Another way of taking a look at this is the divalent ion. So like calcium, magnesium, that has a charge of 2+, excuse me, it needs two ion exchange sites on that bead. So in uncrowded solution, divalent, such as you've just regenerated, there's lots and lots of divalent exchange sites that the calcium magnesium coming into it, it can quickly find a site in which to exchange on. As it gets loaded up or crowded, it gets more difficult to exchange, meaning that think of going to the movie theaters, 2 people, and you get there early. There's all the seats are free and available, so you can sit anywhere you want. So the 2 of you can sit anywhere you want. But if you get there late, you may be in a situation that, well, one of you, you can't sit together because there's only single seats. So if there's only single seats, you're not sitting together. In reference to divalence is that if there's no longer 2 adjacent ion sites, that the divalent cannot get onto the resin. So selectivity decreases as concentration increases. So think of it as there's a lot of crowding on the ion exchange. Monovalent ions, or like lithium, are different. It's that because you have a single site, and there's lots of single sites. So no matter where, again, if I'm going into the movie and it's only me, and there's only single seats, I can sit anywhere in the single seats. So that's key. So monovalent ion selectivity does not change with concentration, but divalent selectivity does decrease with TDS. So bulk ions versus trace ions. Bulk ions accumulate to a significant fraction. Oh, it's 10:52. I apologize. A lot to get through. Bulk ions accumulate to a significant fraction of the ion exchange resin capacities, whereas trace ions don't. So throughput calculations for bulk ions, meaning we're very, very high, gets complicated because of the interactions. Trace removal is less complicated and can be modeled out. So removal of trace ions does not significantly alter the water or the resin resin composition. This allows a simple calculation on capacity. So principle of concentration difference, where the total ionic concentration in the resin is much higher than the ionic concentration, the TDS of the water. So there's more exchange sites in the resin or ionic strength in the resin than the concentration. So at equilibrium, where the resin's been loaded up, the equivalent fraction of the trace ion in the resin will be equal to the equivalent fraction of the ion in the water. So if the thermodynamics have equalized. So the time the resin preference for the trace ions remain a small fraction of the resin's total capacity. So I'm going to just quickly go through kind of the summary of wrapping this up. Since I'm at 10:53, I won't have time for questions. I will indicate this webinar presentation will be available on the website. There's additional materials I'm not going to be able to get through, but please take a look at it because it does get through to conversion. So the takeaway on the ionic selectivity is the concentration of the trace contaminants is relatively unimportant, considering that they're a small concentration in the eluate. The ion exchange has a high ionic concentration. What does affect the selectivity is the TDS of the water. It has profound importance on the efficiencies of that. So it's not necessary for trace contaminants to be the most preferred ion in order to obtain useful throughputs. So in that being said, we're at 10:54. There's some additional slides here. Please take a look at the presentation online. Just to wrap up, is a summary of DLE operating objectives. Is DLE lithium extraction efficiency, that's the removal of lithium from the bulk brine. Eluate lithium purity, this is on the post side, is that we want to minimize the amount of contaminants, water footprint. This DLE process uses a lot of water, so we want to use on the concentration side, we want to use technologies that will maximize the water recovery for reuse back into the process. That's for washing and eluting the lithium off the resin. Energy requirements, that's, if you take a look at ESG, there's an association to the CO2. Also, we want to minimize the amount of energy. And lastly, the carbon footprint is we want to try to achieve the production of green lithium, meaning that our carbon footprint is very small and we can achieve kind of a net zero. So in saying that, I'm going to finish our presentation with that, and we can go into our questions.
Fantastic. Thank you so much, Grant. That was great. The Q&A will now be open. If anybody have any questions, please feel free to type them in. There's nothing yet. Oh, maybe in the chat. Okay, so sorry, Grant, go for it.
Yeah, I'll just reiterate that when you're doing the ion exchange, I mean, there's lots of different ion exchange materials available. Some have functional groups, some are chelants. So there's been a lot of advancements in ion exchange. So I'm going to say the best thing to do is call up your resin supplier, which will have a lot of desktop modeling. Provide them the analysis and the characterization of the concentrated eluate, and they'll be able to guide you and help select the best ion exchange resin for polishing.
So Grant, we do have a question that just came in. Sure. Is FO technology particularly indicated for any DLE technology?
So you would say indicated.
Indicated, sorry.
Industrial FO has been, we've designed IFO into many DLE process flow sheets from mining, but particularly for direct lithium extraction. That occurs on the post DLE side. On the post DLE side for eluate concentrating. So the answer is that it has been designed. And at the final stages of design of acceptance. For reference is that, look, there is not a lot of operating direct lithium extraction plants in the world right now. I think I can count them on my hand. But I think the exciting part of the industry, within a year, you're going to start seeing a lot of finalized demonstration plants and the uptick of commercialization of these DLE processes. So the answer is FO has been designed, probably about a year away of being commercialized.
Thank you. And we have another question. What is the main advantage of FO over RO and OARO?
So RO, number one, is I'm going to say the gold standard. We don't, for disclosure, we don't manufacture ROs. We don't sell ROs. However, RO is a well understood conventional technologies, and it has the ability to pre-concentrate. Remember that the DLE eluate is low in TDS, and if you reference that, an RO likes low TDS environments. FO likes high TDS environments. So you can automatically see there's a synergy between the two technologies. And what I mean by that, if the eluate's around 10,000 ppm, that's right in the sweet spot of an RO. And it can extract water and concentrate, as I said, up to, let's say, a high pressure RO up to 80,000 ppm. Well, that's great. Now I'm going to feed the RO concentrate into the FO. And by using the RO, by pre-concentrating, I reduce the volume going to the FO. If I have reduced volume, let's say I half it by 50%, that means the FO is going to be reduced by 50%. So your CapEx and OpEx goes down. In reference to the energy is an RO, let's say with some energy devices on it, operates around 2, 3, maybe 4 kilowatts per cubic meter. depending on the pressure in the concentrate that you're injecting. So that's why you want to use an RO where you can, because it's a low energy and it's well understood and readily available. FO then takes that, and by the synergies and the complements between the two technologies, the other aspect is that you can then balance the operations, because it's not just the RO and I don't have to push the RO. I'm going to balance the RO operations and the FO operations in which to optimize performance and minimize the operating costs. So again, RO likes low TDS, FO likes high TDS. When you marry the two together, then what you do is you optimize and balance, load share and balance the systems together.
Thank you. And we have another one. What is the difference between RO and FO in terms of flex?
So difference of flex, if I think you're referring to flex energy or flex cooling. So FO, because we require a low grade thermal energy, so 90, let's say 90, 65, 95 degrees, it allows us, because of that energy or thermal requirement, the flexibility we have is that we can pick up that thermal energy from multiple sources. South America, we find that solar thermal, because of the solar irradiance, is a perfect application for that. So solar thermal can be used not only in South America, but anywhere else in the world. The other component is that, well, maybe I have an existing plant and I have steam. So it could be maybe I have a combined cycle steam turbine and I've got some low pressure steam. Well, I can use that steam to drive my process. Or could be geothermal, that my subsurface pump is the brine's coming up at 120 degrees Celsius. I can then use that energy to drive my FO process. If I can use that energy, that means that I'm going to drop my energy requirements by 75% on right away, which is then correlated back to a CO2 reduction.
Fantastic. So going back to the question before that I had asked, the main advantage of FO over both RO and OARO, here is a follow-up. So would I be right to say that FO is competing with forced evaporation after the application of RO?
The answer is yes, that thermal evaporators, been around for a long time. Don't get me wrong, they're used extensively in the oil and gas industry. However, technology advances, and FO was originally designed to broker an in-between RO to a thermal evaporator. And what we found after 10 years of R&D and a lot of investment is that the FO could actually replace the thermal evaporators. So the answer is yes, that industrial FO can replace a thermal evaporator. Osmotically assisted RO is sort of like a synergy or marriage between the two technologies. Rather than doing a 100% FO operation, what you're trying to get this marriage or a hybrid between FO and RO. And as we said, that RO is limited by pressure, the osmotic pressure. Maximum you can go right now is 1700 psi. And that is the TDS and the pressure pushing against that. Osmotically assisted is that, well, what I'll do is I'm going to put a draw solution, salt, rather than just having pure permeate. I'm going to have a draw solution on that side, my feed on that side, and I'm going to use it in an RO operation. So what that means, that the TDS gradient, the TDS from the feed to the TDS from the draw is reduced. That means that the RO pressure can be reduced. Now, you are still challenged is that if I'm now introducing a salt solution to reduce, osmotically assisted, meaning that I'm going to use a draw solution, by introducing that salt solution, it means you still have the challenge at the end of it. I don't have pure permeate. I've got to separate the salt from the water. So in some instances, if it doesn't matter if I have a high salinity solution that I don't have to reuse that water, then that's great. But if I have to reuse that water, then the permeate quality becomes a key factor. So the difference between osmotically assisted RO drops the pressure, but I have a higher salinity permeate, higher TDS, FO. Difference is that I'm going to separate, I'm going to have pure water coming out the back end. There you are.
Fantastic. Thank you so much, Grant. I think that is it for the questions today.
Excellent.
Oh, someone is typing. Do you want to give it a minute?
Sure. We'll take this will be the last question.
Perfect. And as always, the webinar will be available online.
Someone's typing frantically.
Oh, well, there you go. They will follow up with you offline.
Okay, excellent. Well, again, thank you very much, everyone. I apologize. Is that I thought I could get through the slides a little bit faster. That's my fault, but it will be online. Please go through it. If you have any questions, as always, please feel free to reach out to me either through my cell phone, through my email, or contact me online through LinkedIn. Thank you very much for your time. Really appreciate. Hope you enjoyed this the webinar series, and we hope to bring you another one. I think the next webinar series we're going to do more of a deep dive into DLE media operation and selectivity. So that will be the next. Look for that in another month.
Thank you so much, Grant.
Take care. Thank you, everyone. Have a great day.